Hello everybody to the next lecture. Today we are going to do partial derivatives of higher order. So let us define partial derivatives of higher orders, because we already know the partial derivatives are namely f of x, f of y. So we now define for higher orders. If a function f of two variables x and y possessing partial derivatives f of x and f of y are themselves functions of x and y and may possess partial derivatives, these are called second order partial derivatives, and they are denoted by del x of f of x, which is del 2f del x square, or f we will basically denote it by fxx, or del 2f del x square. Similarly, f of xy, f of yx, and f of yy. So let us try to find some partial derivatives with an example. The definition for the partial derivatives will be the same. So let us see the example. Consider the function f defined by f of xy, which is equals to x square minus y square, x square plus y square, where x square plus y square is equals to 0, and 0 where x square plus y square is equals to this is not equal to 0, this is equals to 0. Calculate f of xy at the point 0, 0, f of yx at the point 0, 0. So let us find f of xy at the point 0, 0. So f of xy at the point 0, 0, this means, let's see, so here f of xy means del x of f of y. We need to understand this thing. So first we need to find f of y, and this is at the point 0, 0. So we need to find f of y. That means this is del x, so this is limit h tends to 0, f of y h comma 0 minus f of y 0 comma 0 divided by h. So we need to find f of y at h comma 0 and f of y at 0 comma 0. So let us find f of y at h comma 0. So this will be, again, f of y is del f by del y, and this is at h comma 0. So this will be limit k tends to 0, this is y. This will be f of h comma k minus f of 0 comma 0 divided by k. Here it will be h comma 0. So now this is h comma 0, because h comma 0. So here now what we have is the limit k tends to 0. Now f of hk is this thing, so this is hk, h square minus k square divided by h square plus k square, minus, here we see either so here what we have, the value of y is 0 and x is h, so what we get 0 dot h, which is eventually 0 and whole divided by k. So simplifying, what we get is limit k tends to 0, and we get this k and this k will cancel itself, and we'll get h cube minus hk divided by h square plus k square. But if we put the limit k tends to 0, we'll get h cube by h square, which is h. So f of y at h comma 0 is h. We keep this in mind. We now, what we need f of y at 0 comma 0. So now f of y at 0 comma 0 is we are very much familiar with this thing. So this is limit k tends to 0, and f of 0 comma k minus f of 0 comma 0 whole divided by k, and this will eventually be 0 because this is 0 and this is also 0, and hence f of xy at 0 comma 0 is limit h tends to 0, the above value was h minus 0 divided by h, which is 1. So we get the value f of x comma y. So now we need to find f of y comma x. In the similar manner we find it. So let us see how we do it. So now f of y comma x at the point 0 0, we need to find f of x at the point 0 comma k and f of x at the point 0 comma 0, and simplifying in the similar manner we'll get f of x at the point 0 comma k is minus k and f of x at the point 0 comma 0 is 0. So what we get is f of yx at the point 0 comma 0 is minus 1, and eventually what we get is f of yx at the point 0 comma 0 is minus 1. What we see is f of x comma y and f of y comma x are not same, so this is not equal to f of yx at 0 comma 0. So we have a confusion. Now observation, this was at the point 0 comma 0. We find it normally at all the other points. So let us see. For the point other than 0 comma 0, we verify that f of x comma y is equals to y comma x. So f of x is equals to del x of this value, which is y. We have already done this earlier. So we'll get y x to the power 4 minus y to the power 4 plus x square y square whole divided by this. And f of y and yx is del f of f of x. So we need to find del y of this function, and we'll eventually get x to the power 6 minus y to the power 6 plus 9x to the power 4 y square minus 9x to x square y to the power 4 whole divided by this. And similarly we'll get the same thing for f of xy, and we'll see that it is simple calculation. I think you can try it. So here what we understand, we will now understand when will the partial derivative f of xy and f of yx are equal. For this we state two theorems. So we have very important two theorems to state now, for which we will understand that the value of the partial derivatives f of xy and f of yx are at a certain point when it will be equal. So let us state one theorem right now. So it's known as Cauchy theorem, and it's defined to be, let f of xy be defined in a certain domain D of xy. Let a b belonging to D be any point in the domain. Suppose, so what this says is del f by del y exists in some neighborhood of AB, and del 2f del y del x is continuous at the point AB. Then Cauchy theorem ensures that the existence of del 2f del x del y at that point and further they are equal. So what this says is either of del x and del y, so either del f del x del y or del f, so let us make a line, del f del x, these two exist in any neighborhood of that point AB. So either this exists or this exists, we need only one. And the other, what it says is del y del x, and in this case del 2f del x del y, either of this is continuous. This must be continuous in the neighborhood AB. So if this happens, then this ensures that there exists del 2f del x del y in this neighborhood, and in this case there exists del 2f del y del x in this neighborhood, and what it ensures is del 2f del x del y is equals to del 2f del y del x. So this is Cauchy theorem. So we now state. So now we do Young's theorem. So let us understand what this Young's theorem says. So let f of x, y be defined in some domain D in R2 and AB belongs to D. So there is a domain D in R2 and so there is a point AB in D. So what does it, let us read first. So what does it say? If the partial derivative f of x and f of y exist in some neighborhood of AB and if they are both differentiable at the point AB, then f of xy and f of yx are equal. So Young's theorem says f of x and f of y both exist in AB and that they are differentiable. Moreover, they must be differentiable at AB. Then f of xy is equal to f of yx at AB. So these are the two theorems, Square's theorem and Young's theorem. So these let us understand a note. It is worth noticing that if the condition of Young's theorem or Square's theorem are satisfied, then f of xy is equals to f of yx at AB. But if the conditions are not satisfied, then the equality may or may not occur. For this we give an example. So let us see for the example. So again we have the popular example what we had done previously. So here f of xy is equals to x square minus y square, x square plus y square when x square plus y square is equals to not equal to 0, and 0 when x square plus y square is equals to 0. So previously what we had obtained was f of x at xy was y x to power 4 plus x 4x square y square minus y to power 4 x square plus y square whole square when this and this. So we had done this and we found this also. We had found all this. So let us understand. By putting y is equals to mx in f of yx, here if we put y is equals to mx, then we get 1. So let us understand. So we had f of yx at any xy was x power 6 plus 9x to the power 4 whole square minus 9x y to the power 4 y to the power 6 whole divided by x square plus y square whole cube. So here we put y is equals to mx and let us understand what happens. So f of x at x mx is equals to, we'll get 1. So this is x to the power 6 9 m square x to the power 6 plus 9 m to the power 4 x to the power 6 minus m to the power 6 x to the power 6 whole divided by x square plus m square x square whole cube. So here what we get, x power 6 is common here, 1 plus 9m square plus 9m to the power 4 minus m to the power 6 whole divided by x power 6 1 plus m square whole cube. So we get a function of m only, and m specified arbitrarily is different for different values of m, hence the function does not exist. So the limit does not exist tends to a unique limit. So by this, as this does not exist, and we can also prove that f of y at same point does not exist. So it can similarly prove that f of xy is also not continuous at this. So we here see that f of yx is not continuous, and similarly we can see that f of yx is not continuous. But so this is the thus the condition of Square's theorem is not satisfied. We can further prove that f of x and f of y are not differentiable at 0 0, so the condition of Young's theorem are not satisfied. But we had previously seen that except for the point 0 0 these were equal. So we now do one more example. So consider a function f defined by f of xy is equals to x square y square divided by x square plus y square when x square plus y square not equal to 0, and 0 when x is equals to 0, y is equals to 0. So here we need to find the partial derivatives and investigate whether they are same or not. So here we see that f of x at the point 0, 0 is, so we have already done this. So this is limit h tends to 0 f of h comma 0 minus f of 0 comma 0 divided by h, which is equals to, so at h comma 0 this value is 0, so 0 minus 0 divided by h, which is 0. Similarly f of y at 0 comma 0 is 0. For xy not equal to 0, f of xy is equals to 2x y to power 4 x square plus y square whole square. So let us understand this. So we need to find f of xy. So this is differentiating with respect to x partially f of xy. So let us understand. So differentiating this function partially with respect to x. So this is u by v rule. So this will be 2xy square x square plus y square minus 2x x square y square whole divided by x square plus y square whole square. So u by v rule. So this is our u, x square y square is u, and x square plus y square is v. So this is u, this is v. So u dv, so u v du minus u dv divided by v square, right? So v, this is v du, again dv u whole divided by this. So what we get is 2x x cube y square plus 2x y cube minus 2x cube y square whole divided by x square plus y square whole square. So this and this cancels and we get 2xy, or this is x power 4. So we get this thing, 2x power 4 xy to power 4 x square plus y square whole square. And similarly we will get f of y is at the point xy is 2x to power 4 y x square plus y square whole square. And again we know that f of y at the yx at the point 0, 0 is limit k tends to 0 f of x at the point 0 comma k minus f of x at the point 0, 0 divided by k, which is 0. And similarly we can see that the function f of xy at the point 0 comma 0 is 0. So as both are 0, so we have both are equal. Now we see that f of yx at the point xy is, again we differentiate this thing, we get 8x cube y cube divided by x square plus y square whole cube. This is a simple problem. So now putting y is equals to mx, so here what we get is limit x tends to 0 y tends to 0 f of xy yx xy at the point xy is not equal to 0, but it is equal to 0 here at the point 0, 0. So f of yx is not continuous at the point 0, 0. We can verify that f of xy is also not continuous at the point 0, 0. Thus the condition of Cauchy's theorem are not satisfied. We shall now show that the condition of Young's theorem are not satisfied. So we show that condition of Young's theorem not satisfied. So f of x at the point 0, 0 is limit h tends to 0 f of x h comma 0 minus f of x 0 comma 0 divided by h, which is 0. Now f of x is differentiable at the point 0, 0. So f of x h comma k minus f of x 0 comma 0 is equals to f of x comma xx at the point 0, 0 dot. So this is the condition of differentiability, h f of x y 0, 0 dot k plus epsilon 1 h plus epsilon 2 k. Here epsilon 1 and epsilon 2 must tends to 0 and hk must tend to when hk tends to 0 0, or 2h k to the power 4 h square plus k square is equals to epsilon 1 h minus epsilon 2 k. Putting h is equals to r cos theta and k is equals to r sin theta, we get 2r to the power 5 sin theta cos theta r to the power 4 is equals to, so we put these values here and we get 2 sin theta cos theta, as this and this cancels, and here we have one more r, so this cancel and we get 2 sin theta cos theta is equals to epsilon 1 sin theta plus epsilon 2 cos theta, and hk tends to 0 and 0 0 is eventually equivalent to r tends to 0 or theta remains arbitrary. That is, limit r tends to 0, 2 sin theta cos theta is equals to limit r tends to 0, so which is limit hk tends to 0 epsilon 1 sin theta epsilon 2 cos theta, but we know that epsilon 1 and epsilon 2 tends to 0 as hk tends to 0 0, hence we get 0. Therefore 2 sin theta cos theta is equals to, which is impossible if theta is arbitrary. So this proves that f is not differentiable at 0 0. Similarly, it can be shown that f of y is not differentiable at 0 0. Thus the condition of Young's theorem is also not satisfied. We have thus shown that neither the condition of Scott's theorem nor those of Young's theorem are satisfied, yet f of x is equal to f of y at the point 0 0. So what we conclude is, if the conditions hold, then the equality hold, but if the condition does not hold, it does not imply that equality does not hold either. So this much for today's lecture. Thank you. Thank you for watching this video. For any queries, join my group in the description, and here you can find the soft copy of the notes of the lecture and update of the next lecture. Do like and comment and share with your friends. Thank you.